Lesson: Supervised Learning, Regression and Classification Techniques. Supervised learning, a critical branch of machine learning, encompasses two primary techniques: regression and classification. These techniques underpin a wide array of applications, from predicting housing prices to diagnosing diseases. Mastery of these methods is essential for professionals seeking to harness the power of artificial intelligence to solve complex, real-world problems. This lesson delves into the intricacies of regression and classification, offering actionable insights, practical tools, and step-by-step applications that can be directly implemented. Regression techniques in supervised learning are designed to predict continuous outcomes. A quintessential example of regression is predicting house prices based on features such as location, size, and age. Linear regression, one of the simplest and most widely used regression techniques, models the relationship between a dependent variable and one or more independent variables by fitting a linear equation to the observed data. The strength of linear regression lies in its simplicity and interpretability, making it an excellent starting point for beginners. However, in scenarios where the relationship between variables is not linear, other techniques such as polynomial regression or support vector regression might be more appropriate. Polynomial regression extends linear regression by considering polynomial relationships between the independent and dependent variables. This method is particularly useful when data exhibit a non-linear pattern, allowing for a more flexible model that can fit curved lines instead of straight ones. Support vector regression, on the other hand, is a powerful tool for both linear and nonlinear relationships. By applying the kernel trick, SVR can efficiently handle nonlinear data by transforming the input space into higher dimensions, where a linear regression model can be applied. SVR is particularly effective in situations with high-dimensional data and is supported by robust frameworks such as scikit-learn and TensorFlow. Classification techniques, contrasting with regression, are aimed at predicting discrete outcomes. Common applications include email spam detection and image recognition. Logistic regression, despite its name, is a fundamental classification technique used to predict binary outcomes. It models the probability of a given class or event, such as pass-fail or win-lose, using a logistic function. The logistic regression model is both simple to implement and computationally efficient, making it suitable for real-time applications. Beyond logistic regression, more sophisticated classification techniques include decision trees, random forests, and support vector machines. Decision trees, as their name suggests, use a tree-like model of decisions and their possible consequences. They are highly interpretable, and their rules can be easily visualized, making them a popular choice for exploratory data analysis. Random forests, an ensemble learning method, build multiple decision trees and aggregate their results for more accurate and robust predictions. This method is particularly effective in handling missing data and maintaining accuracy when a large proportion of the data is missing. Support vector machines, similar to SVR, are powerful classifiers that work by finding the hyperplane that best separates the data into different classes. SVMs are particularly effective in high-dimensional spaces and are versatile, as they can use different kernel functions to handle linear or nonlinear data. The scikit-learn library offers an accessible platform for implementing SVMs with various kernels, enabling users to experiment with different configurations to achieve optimal results. The practical application of these techniques requires not only theoretical understanding, but also proficiency with tools and frameworks that facilitate their implementation. Scikit-learn, a Python library, is a comprehensive resource for machine learning practitioners. It offers a wide range of supervised learning algorithms, including linear regression, polynomial regression, decision trees, and SVMs, along with utilities for model selection, evaluation, and pre-processing. TensorFlow, on the other hand, is a powerful framework that supports more complex models and deep learning applications, extending beyond traditional supervised learning techniques. To illustrate the practical application of supervised learning techniques, consider a case study of a financial institution aiming to predict customer churn. The institution can employ logistic regression to model the probability of a customer leaving based on features such as transaction history, customer service interactions, and demographics. By using scikit-learn, the institution can pre-process the data, train the model, and evaluate its performance using metrics such as accuracy, precision, and recall. Additionally, the institution can experiment with more complex models such as random forests or SVMs to improve prediction accuracy and gain deeper insights into the factors influencing churn. In another example, a healthcare provider may utilize regression techniques to predict patient outcomes based on historical data and medical records. By applying linear regression, the provider can estimate continuous outcomes such as hospital stay duration or recovery time. However, if the data exhibit nonlinear patterns, polynomial regression or SVR might offer better predictions. The provider can leverage TensorFlow to build and train these models, enabling the integration of more complex neural network architectures if necessary. The effectiveness of supervised learning techniques is often evaluated using statistical metrics. In regression tasks, common evaluation metrics include mean squared error, root mean squared error, and R-squared. These metrics provide insights into the model's accuracy and its ability to generalize to unseen data. In classification tasks, metrics such as accuracy, precision, recall, and F1 score are used to assess the model's performance. These metrics are particularly important in imbalanced datasets, where accuracy alone may not provide a complete picture of the model's effectiveness. The choice of technique and evaluation metric largely depends on the specific problem and the nature of the data. For instance, in a highly imbalanced dataset where the minority class is of significant interest, precision and recall might be more informative than accuracy. Practitioners must carefully consider these factors and adjust their models accordingly to ensure optimal performance and meaningful insights. The journey to mastering supervised learning is iterative and requires continuous learning and adaptation. Professionals must stay abreast of the latest advancements in machine learning techniques and tools, as well as emerging challenges and opportunities in their respective fields. This lesson has provided a comprehensive overview of regression and classification techniques, highlighting their practical applications and the tools available to implement them effectively. By leveraging these insights, professionals can enhance their proficiency in supervised learning and apply these techniques to tackle complex, real-world problems with confidence and precision.